welcome to the session. In the part 2 of reinforcement learning, we will be discussing some of the important algorithms with respect to reinforcement learning. I'll try to keep it as simple as possible from the point of view of exam. So coming to the first model, that is Markov decision process. So before we get into Markov decision process, we need to first understand what is Markov chain. So MDP or Markov decision process is an extension of Markov chain, which is actually a stochastic process satisfying the Markov property. Let's say I am building a Markov chain with two states. Let's say I have two universities here, University A and University B. So 80% of students of University A leave for University B for getting their master's degrees. So therefore only 20% are remaining in University A for further studies. Similarly, 60% of students of University B go to Universities A for further studies, and therefore only 40% are remaining back in University B. Therefore Markov chain for this example is as shown. Okay, so let's write two states. Let's say this is University A. This state A represents the University A, and state B represents the University B. So states are represented as nodes, and the transition edges are nothing but the transition between the nodes. So how do we represent this? Is number of students moving from University A to University B is 80%. So let's write the transition as 0.8. Number of students moving from University B to A is 60%. So let's write it as 0.C. 20% students remain back in University A. Therefore, the transition is edge value is 0.2. Similarly, 40% students remain in University B. Therefore, the edge value is 0.2. So for this Markov chain, we can write a transition matrix. How do we write this transition matrix? Is P is equal to, let's say this is University A, these are the values of University B. This is again, this row represents A and this row represents B. Therefore, transition from A to A, that means students remaining in University A is 0.2, and students moving from University A to B is 0.8. Similarly, students remaining in University B is 0.4, and the students moving from B to A is 0.6. So this is how you can write the transition matrix. So what is important is the sum of the rows should be 1, and the row of the matrix we call it as a probability vector. So what is important here is these are the states and this is the transition. So basically this is nothing but your Markov chain. So based upon this, right, we have one more equation which we call it as U. U is the probability vector that represents the initial state of Markov chain. So the probability of the chain in state S after n step is the ith entry, which we call it as UN plus 1 is equal to UN into P. Let's understand this better with a problem. So the same problem with respect to the universities. So how do we represent the Markov chain for the same university problem? Let's say the starting distribution is U0. The starting distribution is U0, that is 60%, 40%. This is for University A, right? And this is a Markov chain. So this is our transition matrix. So what is the prediction? The question is, what is the prediction after 1 year? How many students are going to be there in University A? How many are going to be in University B? So the prediction after a year, we write it as U1 is equal to U0 into P, where U0 is the initial distribution, into P is the state transition matrix. So based upon the equation which we just learned. So U0, you write it as 60%, that is 0.6, 0.4, and this is the transition matrix. We just multiply these two matrices and we get the value as 0.28 and 0.72, which means that after first year, the hold of the universities A will be 28% and hold of University B is 72%. So this is obvious because 80% of the students have shifted from A to B. Already 80% have shifted. Therefore, the whole year in how many students will remain in University A after first year is 28%. How many students will remain in B is 72%, because a lot of students move from A to B. That's the reason. After second year, what is the prediction after second year is, right, U2 is equal to U1 into P. We already found U1. So just write down the same U1 here and the transition matrix remains as it is. Now after multiplication, these are the values we get. So, which means that after first year, the hold in University A is 34%, 34.4%, and the hold in University B is 65.6%. Now let's go into, that was about Markov chain. Let's go into Markov decision process. As I said, MDP is an extension of Markov chain. So basically, in short, you can say MDP is a Markov chain with rewards. So we have here an agent and environment. So MDP relies on environment. It depends upon the actions taken by the agent and it depends upon the rewards. So these are the components of MDP. You have a set of states, you have set of actions, you have reward functions R, you have policy pi, which we have learned in the last session, which is nothing but the action which is taken by the agent, so as to get the maximum reward, right? And value V is basically identifies the reward return at each specific state. So what is the return, what is the reward which is returned at a specific state? That is called as value V. And this is a simplified structure of MDP. So nodes are nothing but represent the nodes of the graph, nothing but represents the states, and the edge represents the transition. And each edge is associated to the static probability, which we just saw in the previous problem. So let's take a case study again to understand this better. Suppose there is a hungry antelope in a sanctuary which is looking for food, and it comes upon mushroom. There is mushroom on the right side, cauliflower on the left side. If the antelope eats mushroom, it will receive water as a reward. If it eats cauliflower, there is a lion nearby. So the antelope has to learn to choose the side of mushroom rather than the side of cauliflower. So agent here is the antelope. So it is a decision maker. Decision is made by the antelope. The environment is nothing but the surroundings. In this case, wildlife sanctuary. And the agent is performing different actions depending upon the situations. So the situations are labeled as states. And the action performed by the antelope, that's nothing but an action. Based upon the action, it will receive a reward, which can be a water, or it receive a penalty, which can be the lion. So agent will repeat the process over time until it learns the optimal action at each state. So what's the Markovian assumption is, MDP is based upon the Markovian assumption, or the Markovian property states that the probability of reaching a state ST and getting the reward RT depends solely upon the preceding states ST minus 1 and rewards RT minus 1. And all other previous states are not important. So it just depends upon the preceding state, the previous state. So it states the probability of reaching a state ST plus 1 depends upon the state ST and not upon all the other previous states. So here S dash and S. S dash is a new state, S is the old state. A is the action, R is the reward. Now the aim here is the aim of MDP is to maximize the rewards. The transition is from one state to another state, and agent will manipulate the environment. So therefore the state transition probability is given like this. That is, the probability, state transition probability is nothing but the state, right, ST plus 1, which is S dash is the new probability and ST is equal to S. S is the old probability. So the new state depends upon the previous state S and the previous action A. So that's it about MDP. So you can also say expected value reward. Expected value reward is the reward RT plus 1 also depends upon the previous state S and the previous action A. So coming to after MDP, what next? After MDP, you train and test your recommendation system, right? So once the MDP is modeled, you train and infer, right? Take an inference. So you train the system repeatedly for achieving the goal, which we call it as learning. So once the training model is done, you make an inference, and at the deployment level, you training and inference actually goes hand in hand. So now there are two problems. What are the two problems in reinforcement learning? So as we saw that reinforcement learning is all about trial and error, right? You do the trial, you learn, and learn through a series of actions. You make mistakes, you learn, you get rewards also, you learn, right? So there are two sub problems in reinforcement learning. The first one is prediction of total reward or return, right? So now you have to predict what is the total reward or total return. Now that requires formulation of what are the states and what are the values which you have achieved in each state depending upon the reward. The second so that can be a problem. So it's not easy to estimate the state value function. If you want to estimate what is the value at a particular state, you will have to use something called as temporal difference in learning. The second one, so prediction is a problem. Predicting the state value function is not easy. The second one is improvement of the policy. As you keep doing actions, you maximize the rewards, right? So policy, as I've told, it's nothing but an algorithm. And your algorithm, as you keep learning, the algorithm also has to you have to keep updating. You have to keep improvising your policy. So that is also a big problem. So as you keep learning, as the agent keeps learning, the policy has to be updated. So that is also another problem in reinforcement learning. Now this is a very common question. Explain multi-arm bandit problem in reinforcement learning. Now this is a major problem encountered in reinforcement learning. Let's understand this with an example. This is a 5-arm slot machine which we normally see in a casino. So let's say in a gaming parlor we have 5 machines like this. So there are one lever for each machine, right? So when you do not know which lever when activated will give maximum rewards. So let's say each lever, either it will give money in the range of $1 to $10. Now you have fixed number of attempts. Within that fixed number of attempts, you have to achieve or get the maximum money. So there is a limited chance, right, to get the money. So the point here is which lever you have to activate for maximum profit. So now the lever that returns average return more than other one is the best slot machine. So how do you formulate this problem mathematically is, let's say I have k number of chances to access this n-arm slot machine, and let's say the associated rewards for each machine, I will associate a reward. So for the, let's say this reward for this machine is R1, this is R2, and so on. So you have to find the function, you have to come up with a function. The function is called as action value function. Action value function is you perform an action, what is the value that you get, or you also call it as Q function. And based upon that value, we again take a action A. So this is a formulation in terms of mathematical sense. So you can say the total Q value function is R1 plus R2, that is sum of all the rewards divided by number of chances that you have, and the Q is basically the maximum value. The maximum value we are going to choose to get the maximum reward. The maximum Q value means you have maximum chances of getting the money. So the best action is nothing but the highest Q value, and it is an indicator of the good quality. So let's do a problem on this. So the same slot machine is chosen, where assume a slot machine that is chosen 5 times return awards. So these are the awards. So what is the quality of this action? So what you have to do is, these are the rewards. So let's say I have 5 slots and each slot is giving this reward. First slot is giving the reward 1, second slot is giving reward 2, third one is giving reward 0, fourth one is giving reward 7, fifth is giving reward 9. What is the quality of this? Just add it up together. So this is a formula which we just saw, sum of rewards divided by k. So this is nothing but 1 plus 2 plus 0 plus 7 plus 9 divided by 5. So 3.8 is nothing but the quality of the action. Now very important question, what's the difference between exploration and exploitation? So next few algorithms we will see where in one they either use exploration or exploitation. What is exploration is, the agent is trying to improve its current knowledge about each action through exploration. The agent is exploring all the actions, even if results is suboptimal. So basically it's an adventurous method. Whereas in exploitation, as the word itself says, it's a greedy action to get the most reward by exploiting the agent's current action pair. So the agent is using current knowledge and it keeps exercising that option repeatedly. So suppose in the same previous example where we saw the slot machine, if the algorithm is using exploration, then the agent will explore all the levers, all the machines, and find out which is giving me the best reward. But if you're going for exploitation, then the algorithm knows, let's say the machine 3 is giving me $5, so it keeps exercising only that option, keeps working only on the third machine. So therefore exploitation is not adventurous, and mostly it is suboptimal. It will not really go for the best solution, it will go for suboptimal solution. So what is the best method is a balance between exploration and exploitation. And one such algorithm which we will learn now is epsilon greedy method, where you will see a balance between exploration and exploitation. Let's learn the greedy approach. So in greedy approach, we pick the best action, and it works on the principle of exploitation, that in the sense greedy. It is going to find, let's say I know machine 3 is going to yield, the agent knows machine 3 is going to yield $5. It may not be the best, but then it keeps exercising the same machine. So it basically works for suboptimal solution. So fifth lever returns more money, then keep using it again. It check the first lever, it gave $5. The second lever gave $2. The third lever gave me $10. So it keeps working on the third lever only again and again. So that's called as a greedy approach. So you try to take maximum money, keep working on the same lever to get the maximum money. That's called as a greedy approach. So as I said, it works for solving optimization problem, and the objective is to maximize or minimize the objective function. And there are two properties here. Greedy approach works for optimal substructure problems, and greedy choice property, that means it's a combination of where it uses greedy approach to generate all the candidate solutions. So the two properties are optimal substructure problems and greedy choice property. So let's take an example for this. Let's say I'm going to a cashier and asking him a change for ₹100. Definitely you would not prefer to get 100 1 rupee coins. What would you like to receive? Something in highest denomination. So let's say the cashier has denominations of ₹1, ₹5 and ₹10, and I need change for ₹17. So I want to minimize the number of coins. My goal is what? I need the change, but I want to have minimum number of coins. So my objective is to minimize the number of coins. So what is the solution? What is a candidate solution? Let's say for 17 rupees I have one. What I will do is I will take one 5 rupee coin, two 1 rupee coin. So that would be 5 plus 7, and 10, this has to be 10 1 rupee coin. So what will happen here is 17 I will get here. I think this has to be changed. I'm going to take 10 1 rupee coins, 1 5 rupee coins, and finally I will get ₹17 like this. Okay, so I need a change for 17 rupees. So I will take 10 1 rupee coins, 1 5 rupee coin, and 2 1 rupee coins. So basically I will be doing selection based upon the largest denomination. So highest denomination is let's say 1 10 rupee coin. That would be correct. So to get change for 17 rupees, I will take 1 10 rupee coin, 1 5 rupee coin, and 2 1 rupee coins. So basically I am doing applying my method of largest denomination here. So largest denomination in this case is 10. So that's an example of greedy approach. So where we are trying to work on the same problem again and again. But the problem with greedy approaches, it's a short-term strategy. So there's one more extension of that. Extension of greedy algorithm is epsilon greedy algorithm. So greedy algorithm was basically employing only exploitation based approach. But epsilon greedy algorithm will make a trade-off between exploration and exploitation. So what is the use of this algorithm is, it is applying both exploration concept. It is going on, it's going to explore what are the different possibilities. It is also going to use exploitation approach where it is trying to find a suboptimal solution. So the use of this is, you will have a trade-off, you will make a good choice, you will have a good balance between exploitation and exploration, And if I use this, I can overcome the problem of multi-armed bandit problem, which we just saw. And this epsilon greedy algorithm is very commonly used in reinforcement learning. So let's look into the algorithm. Let's say let's generate a random number p in the range of 0 to 1. Let's generate a number p in the range of 0 to 1. And suppose, let's say the p value is 0.7, and I will choose the epsilon value as 0.5. If 0.7 is greater than or equal to 0.5, then the algorithm chooses the action with the highest reward. If 0.5 is less than 0.7 is less than 0.5, then it will choose other actions randomly. So basically, based upon the epsilon values, you choose your actions and you repeat your actions. So what you observe here is we are trying to explore as well as exploit. I am exploring within a certain range. I am doing exploration of all the possibilities within the range of epsilon. So what is important to decide here is what is the epsilon value. As long as you reach epsilon value, you will be exploring. Once you reach it, you stop exploring and you come for decide the action which will give me the highest reward. So coming to different types of reinforcement agent, these are the 5 different types of reinforcement agent. The first one is value based approach. The goal here is to optimize the value. As I said, every action will have a value. So I have to optimize a value. The value, so basically it's a function which will return the maximum expected future reward. And the agent will get at each state discounted by a discount factor. Discount factor is gamma, which we discussed in the last video. So the second approach is policy based approach, where the goal is to find the optimal policy. The policy is represented by pi. So you have to find which is the best policy for the agent to take the action. So basically it's represented, we use a function. Basically this is also a function which maps a state to a probability distribution of all possible actions. So the goal here is to find the optimal policy to map each state to the best action. The third approach is actor critics. Basically this is a combination of value based approach and policy based approach. So here the actor will learn the policy and the critic will learn the value function. So basically this approach will give a good balance between exploration and exploitation. The fourth one is model based approach. In model based approach, the model is there. You know the model is there. So you construct the model for the environment. For example, we just learned Markov decision process is a model based approach. An example is chess playing agent, where you know there is a model, where in that model you specify the rules of the chess, right? So the rules of the chess you write in the terms of an algorithm, so that becomes your model. The fifth one is model free. That means there are no models here. So here you need some methods. There are no predefined models. So definitely you need some methods which can simulate the model virtually, right? So I will need some agents which will learn directly from experience without explicitly building a model, right? And in some cases I can use some approaches to simulate the model, like temporal differencing you can use, and Monte Carlo methods I can use to simulate the model. Q learning, which we will learn next, and policy gradient methods are an example of model free methods. So how do you select your reinforcement algorithm? So many algorithms we are learning, many more are there. So you choose your reinforcement algorithms based upon the criteria of the availability of models, based upon the environment and nature of the updates. So let's say I have a model already, my environment is static, then I go for dynamic programming. If I don't have models and if the environment is also very dynamic, and if the environment is existing, then I go for SARSA algorithms, or I can go for temporal learning or Monte Carlo methods. If I don't have a dynamic, if the dynamic environment is not present, then offline, we call it as off policy learning, Q learning. So let's learn next Q learning and SARSA. So Monte Carlo methods, as I said, here you do not have any prior information of the environment. There is no information of the environment. All the information is collected by experience. So for example, chess game, right? We repeatedly play the game of chess, right? And receive a positive reward or a negative reward. So basically we learn here from experience. So that is Monte Carlo prediction reinforcement learning method. So here in Monte Carlo, we assume that we don't have any model. Basically we learn from experience and simulation. Each experience is divided into episodes. and each episode is nothing but a sequence of states starting from the starting state to the goal state. So there are some Monte Carlo assumption. All the episodes should terminate, and it uses value action function, and it collects the rewards at the end of each episode. So here we find the maximum expected future reward. So this is the mathematical approach to Monte Carlo policy evaluation. The goal here is to learn the value function from the episodes of experience under a policy pi. So the value function is given as V pi of S is equal to E pi GT given ST is equal to S, where V is nothing but the value function and G is nothing but you're finding the values function at every, you're finding the value for every experience, and these are the sequence of states. So basically it's an incremental update. So you go on incrementing your value for each state. So V of ST is equal to V of ST plus alpha into GT minus V of ST. So basically it's an incrementally you update your value function. So the algorithm for Monte Carlo approach is, given a policy pi, you select a state S, you generate an episode, you compute the average, then you update the returns and start the new episode again and repeat for all the episodes. The next one is Q-learning algorithm. As I said, Q-learning algorithm is a off-policy method. So this is an example of model-free reinforcement learning algorithm. So if you look at this diagram here, I have an input apple. I'm giving it to my system. My system is saying that it's a mango. So what feedback will I give? No, wrong, it's an apple. And that is learned by the system, and the next time it says it's an apple. So it's a reinforced response. So the core idea of Q-learning algorithm is we build a Q table where we storing the values of Q. Each Q value will estimate how good it is to take a specific action. So over time, the agent will keep updating the Q table and you use the feedback it receives. So there are four key components of Q-learning. You have something called as Q values, where you represent the Q values which represents the rewards for taking an action. You have rewards and episodes. Agent will move from one state to another state by taking the actions and receiving the award. Temporal difference or TD, where this is the agent is updating the Q value using this formula. So Q of SA is Q of SA plus alpha into R plus gamma of Q S dash A dash minus Q SA, where S is the current state, A is the action taken by the agent, S dash is the next state, and A dash is the best next action in the state S dash, and R is the reward. Gamma is the discount factor, basically giving a balance between immediate rewards and future rewards, and alpha is the learning rate. Now the fourth component of Q-learning is epsilon greedy policy. As we have already discussed, epsilon will try to achieve a balance between exploration and exploitation. So basically epsilon will give us a, when the probability is less than 1 minus epsilon, it's an exploitation method. Until then it does exploration. So how does it work? There are four major steps. First, you define a state S. The second one is agent will select an action. The third one is action is executed and the environment responds. Then the algorithm will update the Q table and then the policy is refined. So this is an algorithm. I first have a state. I have my Q function initially is 0. Then for all the states and all the actions, I will make the Q value as 0. Now I'll go on repeating. I will select a state randomly. I will choose an action. I'll perform an action. And if the reward is greater than 0, I go for the next state. Then I update my Q function using the formula which I just discussed. So this process will be repeated, right? And at the end of every at the end of 7th state, I will be calculating the Q value using the Wellman equation, and the action will be repeated until I get the maximum value of Q. So the maximum value of Q function is the best action. The last one is the SARSA algorithm, which stands for state action reward state action. It's a on policy learning algorithm. What we learned before Q learning was a off policy method. SARSA is a on policy method. Now here also we have the same kind of component, state, action, reward, next state and next action. The difference here is in SARSA algorithm we update the Q value for a given state action pair. The major difference here is SARSA is online method. It's an on policy method, whereas Q learning is off policy learning method, where all the other components will remain the same, just like Q learning. So what is important is how it is updated. So here again, the core idea of SARSA is we update the Q value for each state action. What is the differences? You have to note down this. The Q value is again updated using the same Bellman equation, and the main difference is this is on policy method. So the steps are very simple again. You have the same steps. Initialize, you initialize the Q values, choose an initial state S0. Now loop for each episode, right? Set the initial state, choose an action, repeat the actions, right? Take action T, observe the reward, transition to state ST plus 1. You are in the state ST, you go to state ST plus 1 based upon the reward. So you keep moving from one state to another state until you reach the best Q value. So this is the total algorithm for SARSA. For all the states, first initially let the Q value be 0. Initialize the alpha value, epsilon value and gamma value. Initialize the states. Next, you choose the action. Get a new state. Choose an action again based on the epsilon greedy approach. Update the action value function. This is nothing but your Bellman equation. Update the states, update the action, keep repeating until you get the maximum value of Q. So SARSA you can write very similar to Q learning. Only difference is SARSA is on policy method and Q learning is off policy method. So that's it for today's session. Let's meet in the next session on artificial neural networks. Thank you so much.